Okay, welcome back to abstract algebra. Um, in this video, we're going to be talking about another topic from section 2.6. It's called the canonical homomorphism. And so I wrote at the top of the slide there, you can see we have two objectives to accomplish in this lecture. One is that I want to prove that a normal subgroup of a group is, that a subgroup of a group is normal if and only if coset multiplication is well defined. We saw last time that if the subgroup is normal, then coset multiplication is well defined. I'm going to show you that that's actually only if, that the only way coset multiplication is defined is for the subgroup to be normal. All right, so in that sense, normal subgroups are the ones that we can make factor groups with. All right, and then the second goal is to prove Theorem 2.62 in your book, called the Canonical Homomorphism Theorem. The author doesn't use that title, but that's how we'll refer to it. Okay, so those are the two tasks. So let's just get down to it. Take a group G and a subgroup of it. And like I was saying just a second ago, this part we've already done. That we've shown that if n is a normal subgroup of the group G, then the coset multiplication is going to be well defined. All right, so what I want to do is try to convince you that the converse of that is true. So let's suppose then I have some subgroup. I have some subgroup of the group G, it's called N, and let's suppose that this operation of multiplying cosets by multiplying their representatives is well defined in the sense that if you use different representatives for the cosets, you'll always get equivalent answers. All right, so that's going to be my assumption. And then I want to show that N's normal. All right, well, you can take a second if you want to review the definition of normal, but to show that a subgroup is normal, I basically have to pick an element in the group and pick an element in the subgroup and show that sandwich, as we usually call it, belongs to the subgroup. All right, so here's how we're going to go about doing that. Picked my A and my N from the group and the subgroup respectively, and then I'm going to look at this coset product. I'm going to look at the coset containing A inverse times the coset containing N times the coset containing A. All right, and by the way we multiply cosets and the fact that it's all associative, I'm going to get the coset containing A inverse NA, the coset containing that sandwich. Okay, but here is the sort of slicko part. I'm going to change my representative. Actually, let me go like this, just to kind of show you what I'm thinking about here. This coset, the coset containing N, it equals the coset containing the identity because N belongs to the subgroup N. All right, so those two cosets are equal. The other two, they're literally equal. The coset containing A inverse, the coset containing A, those are literally equal. So if I take this product using these representatives, that is the A inverse, the E, and the A, then I get this representative, A inverse times E times A. But that just simplifies to E, and so that's the coset N, all right? But we're assuming that coset multiplication is well defined. So those two answers that we just got, first answer was that one, the second answer was that one, they have to be the same because the coset multiplication is well defined. And two cosets are the same if and only if, a coset is equal to the subgroup if and only if its representative belongs to it. So at the end of the day, what have we shown in this argument? We picked an arbitrary element of G and an arbitrary element of N, and we were able to show that this sandwich belongs to N. That's precisely what it means for N to be normal. All right, so you can kind of keep that in mind, these factor groups that we're studying right now. Last time we had this notion, well, okay, in order to make a factor group, you have to have a normal subgroup, and we just kind of completed the story. It's the only way you can make them. No one can make factor groups with subgroups that aren't normal. All right. So that's one of our goals. Let's take a look at the second one. I forgot that I had written that down there. That is just a summary of what I just said, that a subgroup N of a group G is a normal subgroup if and only if the coset multiplication on the set of cosets is well defined. So normal subgroups are precisely the subgroups that you can make factor groups with. Cool. All right. So I'm continuing to experiment with color here. I hope you like it, but I wrote the Canonical Homomorphism Theorem, the name of it, and the book's number, 2.62 in blue there. I'm going to complain once again about our author. He's kind of doing a notation switch later in the section. So just as a disclaimer, as I write this proof, I'm going to be using this Greek letter eta. That's called eta. Every place, whereas when you read your book, the author is using the Greek letter psi. And I'm not doing that just to torture you, but later on in the next section, 2.7, the author uses psi in some different way, and I don't want them to be confused. Okay, so there's just a little disclaimer that the notation the author is going to write this proof in and the notation that I'm going to write the proof in aren't the exact same. Great. So what is the statement of the theorem? Okay, it's written here next. The theorem says that if you take a normal subgroup of a group G, then there's a function that I'm going to define by sending an element of G to its coset. It's a function from G to the factor group G over N. And basically the nuts and bolts of the theorem is that that function is an onto group homomorphism with kernel N. All right. So the theorem kind of asserts several things. One, that this function exists. Well, it's defined in the statement of the theorem. And then that the function is onto, that it's a group homomorphism, and it's got a certain kernel. So we're going to kind of handle those things separately. And this function eta, it has a sort of a fancy sounding name. It's called the canonical or the natural homomorphism, because I think you guys agree. I'll just sort of highlight over as I say one more time that it's a very natural function. You want to associate an element to a coset, well, associate it to the coset that contains it. So it's natural in that sense. Okay, let's take a look at the proof. It's an intimidating sounding theorem, so maybe your defenses are up, but I think you're going to be surprised at how smoothly the proof will go. Okay, so what do we got to do? We got to show that this thing is, well, among other things, a group homomorphism. So I'm going to kind of start there. We were asked to show that this thing is a group homomorphism. Okay, well, so I have a formula for the function, so I take two elements of its domain, and then I'm going to look at eta of their product. And well, by the definition of that, that's the coset containing AB. N's a normal subgroup. Coset multiplication is well defined. That's the product of the coset containing A and the coset containing B, and that's exactly eta of A times eta of B. All right, so the fact that this map is a group homomorphism, it's built to be a group homomorphism. It's a group homomorphism because coset multiplication is well defined. No problem. All right, what about onto? We were supposed to show that this thing's an onto group homomorphism. Okay, well, for an onto proof, what should we do? We should pick an element of the target, choose a coset. Okay, well, if that's a coset in G over N, then it's represented by an element in G. I've called it A already, and I'm wondering, well, what element would eta map to that coset? Well, it's going to map A to that coset. This function eta is onto by definition. All right. So what else do we need to do? We need to show that its kernel is N. Let me scroll back up here for a second, just to remind you that that was sort of the third component of this statement, is that this function's group homomorphism, we've shown that. It's onto, we just did that, so we got to show what its kernel is. So let's quote unquote calculate its kernel. All right, well, so how do I do that? I always pick an arbitrary element of the domain, and then I start asking myself, what would it mean for that element to be in the kernel of eta? Well, it's in the kernel of eta if and only if eta of it is the identity, and the identity in a factor group, remember, the identity in a factor group is the coset, the subgroup itself, the coset containing the identity. Well, an eta of A is the coset containing A, so we must have those two cosets are the same. That's an equivalent condition to A being in the kernel. But we saw when we were thinking about cosets, properties of them, the only way the coset containing A is equal to N is if A is in N. It's if and only if. So these if and only ifs, they provide pick-a-point proofs of this set equality, right? If you take an element in the kernel, then it belongs to N. So that's that subset inclusion. And then conversely, if you choose an element in N, well, the other implications show that it's in the kernel. So we get the other coset, the subset inequality, or subset inclusion. All right, and those two subset inclusions together mean that those things are equal. Okay, so we're gonna cut it right there for this short video. That was our goal. We wanted to show that subgroups are normal if and only if coset multiplication is well defined, and establish this very important fact that given a group, I'll just sort of summarize here, and a normal subgroup of it, there's always an onto group homomorphism from G to G over N, and its kernel is N. Next time, we'll see why we would want to have such a tool. Okay, thanks for listening. I hope you liked it.